Yes. Thank you, Tomasz. So my name is Peter Kuma. I work at Stockholm University, and I previously studied at Comenius University, where I did my bachelor's degree and master's degree. Then I did my PhD in New Zealand, and now I'm at Stockholm University working as a researcher. And today I'll present broadly on the topic of climate science and climate modeling. And I'll present some of my work, but also I'll present some of the general topics of climate science, which are not necessarily like work that I worked on personally, but are necessary to give you context in terms of climate modeling and climate change. Okay, so I'll start with sharing the slides. Okay. Um, Hopefully you can see the slides. Is that correct? Can you see?
Yes, we can see.
Okay. So the current topic, or like the topic of the presentation, is climate modeling and current research topics in climate science. And first, I want to just introduce you to climate science in general, so that you have an understanding of the later topics that I'll be covering. And so the climate system is something that we study as climate scientists. It consists of various components. We divide it into the atmosphere, ocean, cryosphere, which means ice sheets like Antarctica or Greenland, but also it means sea ice over the Arctic Ocean and sea ice over the Antarctic, so the Southern Ocean, and glaciers over mountains. Then biosphere, that would include any kind of usually non-human life. So that would be organisms in the ocean, especially things like plankton, plants on land, and so anything that can influence climate by uh, either due to like albedo, I'll cover that later, what that means, or chemical exchanges with the atmosphere and ocean. And then we have humans, and that's often treated as sort of separate from the climate system, but it really depends. So humans obviously affect the climate system due to various reasons, like emitting greenhouse gases or aerosols, changing the reflectivity of the Earth's surface by changing the use of land, turning, for example, a forest into a field, or urbanizing land, and so on. And that could be sort of in climate modeling, that could be prescribed from the outside. So we don't really include it in a climate model, or it could be even like maybe integrated. So we can try to predict how humans would behave in the future. But that's not as commonly done as the prescribed method. And then the climate system is not static. It's constantly changing, and it's changing due to various factors that we often call forcings. And that would be solar radiation. So there's sunlight coming from the sun, which warms the earth. There's greenhouse gases which change in the atmosphere, mostly due to us changing the atmospheric composition, and aerosols, which means like a tiny particles in the air due to burning of fossil fuels or organic material and so on. And land use change, I've already mentioned, that's the change of land use due to human activities. And so like in this photo here, like it's an image from a satellite from yesterday, showing the sunlit part of the Earth. It's from a satellite which is in the first Lagrangian point, so it's quite far from the Earth. And like here you can see some of the factors that the climate system is composed of. Maybe like one of the notable ones is the cloud cover, which is very changeable in time and in space. And so that's like one of the very difficult aspects of the climate system to simulate, for example. The Earth is nearly in radiation balance. So that means the sunlight coming to the Earth is almost equal to the thermal radiation that's emitted by Earth into space. And so the planet basically cools or warms depending on the balance of the radiation at what we call top of atmosphere, which is like an imaginary sphere encapsulating the entire Earth. So at the top of atmosphere, we sort of calculate, the incoming solar radiation, the outgoing long wave radiation, or like terrestrial radiation, and the difference is how much the Earth is warming or cooling over time. That could be expressed in watts per square meter. Uh, and the warmer the Earth's surface, the more radiation it emits. That's due to just Planck's law, or maybe you've heard about Stefan Boltzmann's law, which means that if you have any object of non-zero absolute temperature, it emits radiation. And the warmer the object is, the more radiation it emits, and the higher the frequencies of the radiation. And so as the Earth warms due to, for example, global warming, it increases the temperature and increases the amount of terrestrial radiation outgoing into space. And so that's the balancing factor. Like if we, in some way, for example, block the amount of long wave radiation due to increasing greenhouse gases, the Earth's surface warms, but also the amount of Planck radiation increases, and so that restores some of the balance, but usually not entirely. And so like what's like the most changeable in our climate today are greenhouse gases, clouds, and aerosols. And I'll go into these like in more detail. But like greenhouse gases are obviously the main factor today, how we affect the climate. Um, but the clouds then change in turn, like as a response to the warming. And aerosols is like a secondary factor that we also influence. Due to releasing aerosols, we cool the planet because the aerosols mostly reflect radiation into space, like they would reflect sunlight back into space and therefore cool the Earth. And so I'll just go to some of the detail in what it means, like why carbon dioxide and methane are greenhouse gases and why they warm the Earth. And that's because the long wave radiation outgoing from the Earth into space, that's the red line here at like 300 Kelvin. That's an idealized Planck's radiation. That radiation is absorbed by greenhouse gases in the atmosphere, and there are several of them, but the main ones are water vapor, carbon dioxide, and methane. Water vapor is pretty stable in the atmosphere because it's very much tied to the temperature of the air. And so that's not something which we change directly normally, but what we change is carbon dioxide and methane. And so carbon dioxide has these absorption lines at about 12 microns or 15 microns of wavelength. That's pretty much in the center of the thermal emission. And so that means that the molecules of carbon dioxide absorb the terrestrial radiation emitted by the Earth's surface. And that's like due to quantum effects like vibrational transitions in the molecules of CO2 and rotational transitions, and in some cases also electronic transitions, but that's mostly for like higher frequency radiation. And then methane is another greenhouse gas, and that absorbs at around 9 or 8 microns. And because it's a different wavelength from CO2, has a different effect. It's mostly like it's said to be a stronger greenhouse gas, but that's because the concentration is lower, the absolute concentration is lower in the atmosphere. And so the relative change is like causing a bigger effect, because like what happens with CO2 is it saturates the absorption. So once like all the wavelengths are completely absorbed, it can't absorb any more of them. So if only they're partially absorbed, there's still like more capacity for the greenhouse gas to cause more absorption at those wavelengths, if that makes sense. Okay, so that was the difficult part, and now I'll go to some easier parts slightly. So when we measure the radiation balance at the top of atmosphere, which is the imaginary sphere encompassing the entire Earth, we see that it's not in balance anymore, or like it's never really in the balance, but like even in the pre-industrial times when like people were not influencing the climate, the radiation balance was like fairly close to zero over time, like over longer periods of time. But now we see these like large trends, and so these are curves measured by satellite instruments called CIRRUS. And the red line is shortwave radiation, so that's sunlight reflected. That's basically the amount of sunlight which is reflected. And the blue line is long wave, and that means that's the terrestrial radiation. And what we basically see here that the shortwave part is increasing, so that means the Earth is warming due to more sunlight being absorbed. The main reason for that is cloud change. So the clouds change due to increasing temperature of the Earth, and they change in a way that they start absorbing less sunlight, so reflecting less sunlight. So the Earth becomes more absorptive in the shortwave. And in the long wave, we have greenhouse gases which block some of the terrestrial radiation, so it can't escape into the space. And then we have like here, this is like a summary of the trends here. And you can see that, so the greenhouse gases would be under other, but then we have water vapor here, which is another greenhouse gas that increases due to increasing temperature because warmer air can hold more water vapor. And then we have the temperature feedback, and that's something I mentioned before, that's the Planck radiation. If we increase the temperature of the Earth's surface, it starts emitting more radiation due to just the black body Planck's law. Okay, so that sounds a bit complicated, but the main message here is that the greenhouse gases that we affect primarily block some of the terrestrial radiation that increases the Earth's temperature. And then in turn, this increase causes different changes in clouds, in water vapor, in the surface reflectivity, and so on, which amplify the effect of greenhouse gases. So the greenhouse gases are sort of like an initial push, and the other processes are amplifiers, which are in the end much stronger than the initial push that we give to the climate system due to increasing greenhouse gases. Now I just want to mention like how we model the climate. So we use there are many different ways how we can model it, but the main one is using global climate models. And a global climate model basically divides the Earth into some kind of a mesh, and on the mesh it calculates using like Newton's laws applied to fluids. It calculates the flow in the atmosphere and in the ocean. And also it simulates various different other effects like clouds, the cryosphere, land, and so on. And so what we do initially, we divide the climate system into different components, like here that's illustrated for one particular climate model. We turn it into atmosphere, ocean, land, sea ice. And then we separately maybe model chemistry, which, that would be chemistry in the atmosphere, but could be also chemistry happening in the ocean, which relates to even like cycle of greenhouse gases and other things. And then what we want to know from climate models is how the temperature is going to change, what's the effect on weather extremes, how the circulation in the ocean is going to be affected by increasing temperatures, how the clouds are going to change, how much, more rain or snow we're going to get or less, and so on. So we can ask all kinds of questions once we have these models. This is an image from a work that I did before. It's on mapping climate models as a sort of a study of their history and their relationships. So this is just a picture of which shows about 100 or over 100 different climate models. Usually takes several decades to develop a climate model, and that's why it's not usually studied from scratch, but it's evolved. So if some new research center wants to develop a climate model, they usually take the code from someone else and start developing those processes or components that are interesting to them. It could be due to some geographical location, or maybe they want to ask some particular questions about extremes or other things. And so the initial climate models started to be developed in sort of the 1970s. And from those times, more and more models were sort of derived from the original models. And so here you can see, for example, this ECMWF is like a common European model, which was developed starting in the 1980s. And it's being developed until today in sort of various other branches of models. Uh, and this would be like several, we could identify several like climate model families. In this paper, we identified 12 different climate model families. And so that sort of tells us that many of the models are related, but there's still quite some independence in the climate models because there are still like sort of 12 main independent branches of climate models. And they're like all developed in different countries by different research centers. So over time, they tend to diverge more and more. Uh, in terms of climate modeling, can that be done in different ways? The main one is related to the sort of resolution and how many processes are included in the climate model, and whether it's like local or whether it's a global climate model. Um, so normally what's like used for climate projections today is called ESMs, which are Earth system models, and they have a resolution about 100 kilometer on horizontally. But there are some higher resolution ones. One is called LAM, which is a limited area model, which means we just want to maybe simulate a certain region, like let's say Europe. And so we can, use much higher resolution on that specific region. But what's called like we take the boundary conditions from a global climate model. So we take the what's outside of the domain to come from the global model, but what's inside the domain is simulated specifically at a high resolution in the limited area model. And then at the highest resolution, we have something called LESS, which are large eddy simulations, where we use even higher resolution, about 100 meters. And then we can actually start simulating various like smaller eddies happening in the atmosphere. And it's something that's usually used for research. So we might want to ask questions about convection in the atmosphere and turbulence and so on. And so these high resolution LESS models are able to answer those questions. Or sometimes you want to model a city, like what's the circulation going to be like in a city, and then we need like small scale geography of the city and the size of the buildings and everything, and then we use LESS to simulate the flow in a city. And so depending on the complexity of the model, we can even run it on the personal computer. If we take a climate model from, let's say, 1990s, we can easily run it on a personal computer. And the resolution might be about 2 degrees longitude, latitude. So that's like a pretty low resolution, but it's something that's maybe useful for research when we want to like change various parameters often and see the end result. But then as we get to like global models and high resolutions, then we really need supercomputers. So we need like sometimes tens of nodes on a supercomputer, sometimes even hundreds to run a climate model. Like in a time frame that we want, which is usually like we want to be able to simulate several days of the climate system within a day of computations or that sort of range to make it like feasible to calculate, let's say, 100 years into the future. So supercomputing, you might know quite a bit about this. I suppose you might be also users of supercomputing here. So I'll just mention like climate models are usually using programming languages like Fortran, but nowadays some are turning into like Julia, which is like a more modern language for computations and like memory save and so on. But in terms of like doing day-to-day research, we still mostly use Python. Although for climate models, it's less useful because it's too slow to run a climate model. We want to use like as much computing speed as we possibly can get from a climate model. So uh, then Python is not such a great choice. And then when we can, we use GPUs for acceleration, and that's sort of like an ongoing topic to turn the, let's say, some of the fairly old climate models, which were going on from 1980s until today, and using Fortran into models which are sort of hybrid and use both CPU and GPU. And like typically the supercomputing nodes are similar to workstations. You get like 256 gigabytes of RAM, and you get maybe two CPUs, and each CPU has like 64 cores. And then if you want to run a climate model, you ask for allocation of like tens to hundreds of nodes, depending on the scale you need, and wait for a few weeks or months, and then you get your results, and then you can study the model outputs the way you want. And so these are just some examples that the supercomputers that I worked with. One is called Levante in Germany, with just about 3,000 nodes and 14 petaflops, and Maui, which is a supercomputer in New Zealand, which is about 500 nodes and about 1.5 petaflops of like floating point operations per second. Uh, in terms of like resolution versus performance, we want to, maximize the resolution in such a way that we use all the performance available to us. And we can do that very easily by just increasing the resolution. And with increasing resolution, we have to increase all the dimensions, which means the x-axis, the y-axis, the z-axis, and the time step as well. And so it's like, let's say we half the mesh size, and then we increase the performance demand by 2 to the power of 4, because we have 4 dimensions which all have to be halved at the same time to preserve stability, like computational stability. Um, and so this just shows like how many CPU cores we would need with increasing resolution. So as we go from, let's say, 100 kilometers to 10 kilometers to 1 kilometer, we need like increasing amount of CPU cores to, or like we could decrease the throughput, so the number of simulated years per day of computations. Okay. And just want to go back to explaining some of the bits of climate change. So as you probably like all know quite well, there are two main greenhouse gases that are increasing, which is carbon dioxide and methane. So carbon dioxide has been increasing since the Industrial Revolution, which is approximately year 1750, due to just burning of fossil fuels and land use change to a lesser extent. And so we increased carbon dioxide so far by about 50%. And we also increasing methane. And we are increasing methane mostly due to things like livestock, so cows and sheep, which emit methane due to just their digestion, and things like leaks from processing oil and gas, and fields from rice fields as well, from growing rice, and from falling permafrost. So as we increase the temperature of the Earth's the permafrost over Arctic, let's say, is melting, and that releases methane. So both of these were growing very rapidly, and both of them are fairly strong greenhouse gases. And there are some less important greenhouse gases like nitrous oxide from fertilizers and so on. Yeah, but at the same time, we've been increasing aerosols. So we've been cooling the Earth by increasing aerosols. So that counteracts the warming by greenhouse gases. And like there's some secondary effects other than just the temperature. And the main one is ocean acidification. So when we increase the amount of carbon dioxide in the atmosphere, some of the carbon dioxide is going to be dissolved in the ocean water and is turned into carbonic acid, and so that increases the acidity of the ocean, and that's a problem for various animals living in the ocean, which have um, calcium in their shell, basically, which depends on a certain pH of the water. So I've touched upon this a bit. Like climate feedbacks are something which are processes which happen due to increasing or decreasing global temperature. So once we increase the temperature of the globe, various things happen, and they tend to amplify or sometimes dampen climate change, or like global warming, let's say. So the main one is clouds. So once we increase temperature, the clouds tend to be more sparse, and so there's more sunlight absorbed by the Earth, and so there's more warming. And another main one is water vapor. So I mentioned that water vapor depends on air temperature. So once the air temperature is greater, we also get more water vapor in the atmosphere, and water vapor is a strong greenhouse gas, so that amplifies warming. And then Planck feedback, that's the one which I mentioned before, which means that as we increase temperature, there's more terrestrial radiation due to just Planck's law being emitted into space, and also that cools the Earth. So that's the main compensating factor that turns the radiation balance back into zero. Just a broad overview of like the change which sort of has been happening historically, and so this shows the change in climate system which is unrelated to human activities. This is a natural change due to changing orbital parameters of the Earth, but also the solar output over millions of years and so on, and the change of like continents. So the continents on the globe have been moving over time, and so that also has a strong effect on the climate. And so we are currently still in a time period on the paleoclimate time period of cold climate. And what I mean by that is since about 50 million years ago, the temperature has been going down, and that has been, connected to various things like the glaciation of Antarctica. Previously Antarctica didn't have that much ice, and that's due to decreasing temperature, but also it's connected to things like evolution of animals and plants. The decrease of temperature is related to the rise of mammals as species, and that's because they thrive in lower temperatures. The previous time periods were more dominated by reptiles and so on. So the main event that you all aware of is the one which happened 67 or 66 million years ago, which is the KT event, which killed all the dinosaurs. So that's basically the red box here is what happened after. It's called Cenozoic, and that's the current era. So the current era is relatively cold compared to the historical times, like the very far historical times, when the temperatures were like almost 30 degrees Celsius at certain points, whereas now the temperature is about 15 degrees Celsius. But also it means that all the life on Earth has already adapted to these relatively low temperatures on the kind of scale of time of millions of years. Okay. And so what's been happening recently is that due to various like emissions of CO2, mostly and other greenhouse gases, we've been increasing the temperature. So this is the global mean surface temperature anomaly, and we see that the black line is the measured one, and so that's increased by now almost 1.5 degrees Celsius. But at the same time, we've been emitting aerosols, and so the blue line here is the evolution of temperature that would happen only if we were emitting aerosols and no greenhouse gases. So that would be negative. We would actually be cooling the Earth system. And so the end result of greenhouse gases plus aerosols is that we get somewhat less warming than we would get, without aerosols. And so like the main sources of greenhouse gases are from like power generation, so electricity, and transport, so cars and ships and so on. And the other ones are still like contributing significantly, like on the order of 10%. But it's like it's I would say it's a mix of different sources. So there's no single source that's the biggest, or like the power might be sort of the outstanding one, but otherwise it's quite diverse. And that's because obviously we use fossil fuels in all kinds of ways. Plus we change the land, which also that's the change of land is under this one LUCF. And then methane is due to just livestock and some other sources as well. And this is like what it looks like in the last couple of years. So the last 2 years have been like very warm, and that's a combination of factors. Probably one is a strong El Nino, which has been ongoing since last year. But also before there was a La Nina. So El Nino and La Nina are two phases of the major climate oscillation happening in the Pacific. That's a natural oscillation which happens every few years, and has been happening for a long time. So that has nothing to do with human impacts as such. The El Nino time periods are globally warm ones, and the La Nina periods are cold ones. And so that's due to how the circulation is arranged over the Pacific Ocean and in the Pacific Ocean. And so the last 2 years, that's something you can see here in the sort of red and orange lines, which are now statistically way warmer than the previous years. So the gray lines are the previous years, and currently it's still like uncertain why there was such a jump in temperature and whether it's going to persist or not. So we are now at 1.5 degrees warmer than pre-industrial, but that's like a short-term measure. It doesn't necessarily means that's like a breach of the target of 1.5 degrees set by the Paris Agreement, because that's measured over like several decades. So, but that's likely it's going to be breached by 2030 or so. And so this is just on reducing emissions. So there are like you might be aware of the Paris Agreement, where all the nations have decided that they want to pursue reducing emissions in line with limiting warming to either 1.5 degrees or 2 degrees Celsius, relative to pre-industrial temperature. And so in order to achieve this type of limits, we would have to start reducing CO2 emissions very rapidly now. And so these two lines, the green line and the blue line, are the emissions which would have to happen in the future from now to be able to stay within those limits. And the currently implemented policies are the red line. So that's what's the current trajectory looks like. So the current trajectory is nowhere near those targets, basically, currently. Yeah. And so to be like optimistic, I think we do have like various options how to reduce the emissions. They just need to be put into use. And one option is renewables, which are now very inexpensive compared what they used to cost per kilowatt hour, let's say. Nuclear energy and electrified transport, or using less transport, reducing deforestation through reducing the amount of wood and paper used, and reducing methane emissions through changes in how we produce food or what type of food we produce. For example, meat and dairy are very intensive on methane emissions due to livestock emitting lots of methane, and also the keeping the livestock is associated with lots of land use to be able to feed the livestock, and so the land use is also responsible for deforestation and other changes in the land, which usually cause stronger warming. Okay, and geoengineering methods are something that's been proposed recently. but there are many problems associated with geoengineering. The main one is the side effects, which are quite uncertain. But even if they were certain, there would almost certainly be areas on the globe which would be affected negatively by geoengineering, and other areas which would be affected positively. So it would be probably very unequal way how to address global warming, and also a very temporary way as well. And it wouldn't solve, for the most part, it wouldn't solve ocean acidification, which isn't tied to temperature, it's just tied to the concentration of CO2 in the atmosphere. Okay, so I'll just now briefly introduce kilometer scale climate modeling. So recently we've been trying to reduce the resolution of, or like increase the resolution of climate models down to 1 kilometer. So going from, let's say, sort of 100 kilometer range to 1 kilometer range. And that would allow us to resolve various things explicitly in the model, like convection and turbulence. Well, it would help some of the turbulence, but also it would help us to resolve things like storms in the atmosphere and eddies in the ocean. And that would increase the accuracy of the climate models. But it comes at like at a much greater cost in terms of computational power, because as we go to 1 kilometer from, let's say, 100 kilometers, we increase the performance requirements to the power of 4. So that's a huge amount. And currently, these models are under development, and possibly in the next few years or 2 decades, they'll be in production use. So maybe in the next phase of climate projections of the IPCC, there'll be already some kilometer scale models included. Yeah. And now I wanted to play a video, but I'm not sure like how well this is going to work, honestly, but I can try. Uh, okay. So this is from a kilometer scale model, a simulation. Yeah, I'm not sure how well you can see the video on your end, but I'll just say that basically having this kind of high resolution simulation allows us to much better resolve things like clouds, things like storms, eddies in the ocean, and so on. So this, if you see the animation, you could see that the the circulation can be resolved like much better than we would be able to with like current generation of models. Um, okay, let me go back to the slides now. Okay. So now I want to briefly mention AI-based climate modeling. So that's an emerging topic in climate modeling, and there are many like different ways how to do it. But like one of the main ones is the breakthroughs are happening in weather forecasting, and they're using like some kind of like a encoder decoder type of neural networks, which take like a state of the atmosphere or in the ocean in like time step 1, let's say, and they apply the neural network and get a time step 2, like there's time step t plus 1 here. And so we train the coefficients in the neural network in such a way that they can calculate the next time step of the model from the current time step. And the training happens based on existing climate model simulations, or what's called reanalyses, or on satellite observations. So the neural networks basically are trained to try to emulate, let's say, in a way, the existing climate models and our observations. But the advantage there is they can do it much faster. So climate models are relatively slow because there are many equations that need to be calculated. Whereas neural networks, they are quite performance efficient, like, maybe even 100 times more performance efficient than a normal climate model. And so that's a huge advantage. And another way, what we can do is like embed a neural network inside the climate model and let it simulate just some processes inside the climate model. And so in that way, we can speed up certain parts of the climate model and maybe also make them more accurate because some of the parts of the climate models are based on statistical relationship, things like clouds, convection, sea ice processes, and so on are often based on statistical relationship that are first measured in the reality, but we don't have often good equations like from fundamental equations for these parameterizations. I mean, they form, let's say, a minority of climate models, but they tend to be quite important. So that's a possibility for neural networks to be employed there. Okay, now a different topic, which is microplastics. So maybe already know quite a bit about this topic, and it's like a emerging environmental concern due to various bits of plastics being in the environment, and that just happens naturally because we release various kind of plastics in the environment, which break down into smaller pieces. Could be packaging, could be textiles, could be what's called primary microplastics, which are already made small, sometimes for like paint or for personal care products, and so on. And so over time, these end up in the atmosphere and the ocean and the cryosphere. And so that causes various other effects. These are just like a summary of various measurements in the atmosphere of microplastics. Uh, the concentrations tend to be anything from like one piece of microplastics per cubic meter to several thousand. Usually cities have much greater concentrations of microplastics due to just there being more sources. But also the microplastics are transported all over the globe due to atmospheric circulation, due to ocean circulation. And so they end up even in the Arctic, in the Antarctic as well, and in remote oceans. So that's something which becomes a global phenomenon, and it's not limited to just the geographical areas of the sources. And it's just some work that I've been working on, which is quantification how microplastics affect radiation in the atmosphere. So because that's all, microplastics are new constituents that we edit into the atmosphere, they affect solar radiation and thermal radiation by scattering and absorption and by emission. And so due to these effects, they change the radiation balance. It's probably a very small effect, and indeed we showed that it's a small effect. So it's not something that we need to sort of worry about right now in terms of the radiative effects of microplastics. But we could see that over time, if the concentration increases, so by like 100 times the current concentration, then we get effects of like 0.1 watt per square meter. And so then they become important in terms of their radiative effect compared to other aerosols. And so like what we do sort of, we take my theory, me theory, which is a way of calculating the scattering and emission and absorption effects of spherical particles to calculate their optical properties. That's like the graph here, which is like absorption and scattering by wavelength of the radiation. And then we put this into a global climate model, and the global climate model can then simulate the radiation change at top of atmosphere over time, like how what the effect of the microplastics is inside the climate model. And so that's this graph. And yeah, and we had the results published in the journal Nature a few years ago. Moving on, this part is about measurements over the Southern Ocean and measurements of clouds, especially over the Southern Ocean. So that's a project that I was working on while in New Zealand, but now I'm also processing some of the data. So we went on this ship called RV Tangaroa, and we went from New Zealand to the coast of Antarctica. That's like one of the lines here is the voyage. And we measured clouds, aerosols, and other things with oscillometers. I'll explain what that is, and with radiosondes. So radiosonde is like a small package which is launched on a weather balloon and rises up through the atmosphere, and we can measure things like temperature, relative humidity, wind speed, and so on. So we had like all these type of different instruments there. So these first two are lidars, or it's called a oscillometer. So it works by sending a pulse of laser radiation up, and then it measures the amount of radiation which is scattered back into the instrument. And so that's scattered by clouds mostly, but also aerosols. And so then we can get a structure of the clouds from those measurements. And we had a weather radar, which is something which measures precipitation vertically upwards. This is called a helicite, which is sort of a balloon which is tethered, so it's connected with a line to the ship. And on the balloon we had packages which measured various aerosols and temperature and humidity and so on. And this here, that's me launching a weather balloon. So a few times on the voyage per day, we launched a weather balloon with a radiosonde to measure the atmospheric profiles. And we had a UAV, which is this one, also to measure various properties of the air by height. I'll skip the videos because there's not that much time. And so here, this is just the measurement from the oscillometer. So the oscillometer can measure cloud structure. So this is backscattered laser radiation. And so the more backscattered laser radiation we get, the denser the thing in the atmosphere is. And the thing usually is a cloud or could be aerosols. But here is mostly what you see is clouds. And so this is by height. So it goes from 0 to 15 kilometers height. And the x-axis is temperature, time. And so over time, we get a profile of clouds by height. And then what we can do is run a virtual instrument inside a climate model. So we can calculate what an instrument would see inside a model. So this is one specific called ERA5, which is actually a reanalysis. It's not a climate model as such, but it's based on a weather model, but it's also global and includes clouds. And so what we see here is the same time inside the model and the cloud structure, what it would look like inside the model if it were measured by a oscillometer. And so once we have this simulated profile, we can compare these two over long time periods, and we can see what kind of errors we have in the model in terms of cloud simulation. And so that's the graph here, which shows the cloud occurrence by height. So this is a long-term statistics calculated from the cloud mask that I showed in the previous slide. And we compare observations, which is the black line, with various types of models. And then we can see the error in the models by height. So for example, here we see that it's called ICON model, which is a kilometer scale model that's sort of, I described before, the kilometer scale models. That model overestimates the amount of cloud in the first 1 kilometer. And so that in turn causes various kinds of secondary effects on the radiative transfer. You know, if we have like too much cloud in a certain altitude, we get more reflection of the sunlight, but that changes also the the amount of terrestrial radiation which is passing through the atmosphere. And but overall, we see that the models are underestimating the amount of clouds this is over the Southern Ocean compared to the voyages that I showed before. And so that's like a fairly big error in terms of the radiation that it causes in turn, basically. So having too few clouds means too much radiation coming to the ocean surface and too much warming of the ocean. And that in turn affects, the radiation balance of the climate model as well. So it's not something which invalidates the climate model results as such, but it's something which causes the climate model results to be less accurate. And so that's something which needs to be improved. Okay, I don't have that too much time now. So I'll just mention like this another project which was on using machine learning to identify clouds. And we used satellite data from an instrument called Cirrus. And we had like these kind of images from the satellite. And from the surface, we had various station measurements over several decades. And then we could train a neural network to be able to identify different cloud types inside the satellite image. And so the cloud types are initially identified by the observers at the stations. But then when we train the neural network, we can extend the classification to the whole globe because we have satellite images for the whole globe. Whereas the stations are, located mostly at certain geographical locations. And we use like this kind of neural network. It's called UNet, which is it's called like an encoder-decoder network, which first downscales the images into smaller resolution and to what's called latent space. And then it upscales the latent space into the same resolution as it was originally. So we can produce classification for every pixel of the input image. So that would be the input satellite image. And on the output, we get an image which tells us for every pixel what kind of cloud type there is. And so the training is done on the stations. So the stations from, the station data over several decades tells us the cloud types. Okay, I'll skip this one. And so what we get in the end is these kind of geographical distributions of different cloud types. Here it's like condensed into just 4 cloud types: just high cloud type, middle, cumuliform, and stratiform. And so this is from the satellite data. But we can do the same on climate models. So we had like maybe 20 climate models, and for each we could do the same thing and see what the error is in each model in terms of the different cloud types. And so what we did like as the last step, we could calculate the what's called climate sensitivity, which is like a parameter of the model, which identifies how the model is how warm the model is, let's say, or like how the temperature inside the model changes in response to increasing greenhouse gases. So what we do is we double the CO2 concentration in a model, and then we run the model for, let's say, 100 years or several hundred years, and we calculate how it changes the temperature inside the model. So it's the temperature change due to doubling of CO2. And we saw that the models which have lower cloud errors, which are these dots here, have also higher sensitivity than the models with greater error. And so that tells us that the models which simulate the cloud types better in terms of our analysis are the warmer models. And that in turn tells us that it's possible that the models which are warmer and have better representation of clouds are actually the ones we should believe more. But I don't want to go into all the details, and I'm out of time now. So I thank you for your patience, and I can take any questions that you might have. Thank you.
So thank you, Peter, for the engaging and insightful presentation. And if anyone has questions, please feel free to share them now.
Can you hear me?
Yes.
I have a question. This is the last time there are some news about the changing the Gulf stream or other streams. Do you know something about that? It's some hot topic or just rumors?
Yeah, it is actually a hot topic. So that's something that we really want to know because if the circulation in the Atlantic decreases, that means less warm water will be brought to Europe, let's say, and so that will in turn cause cooling in Europe. And the current conclusions, as I know, are that it's still like fairly unlikely that the circulation will decrease in this century. But at the same time, there is some latest research happening in sort of the last year or two, which says it's more likely than the previous studies. So I would say it's still very uncertain. So the international consensus in terms of like IPCC consensus is that it's not a big risk that it will happen in the next 100 years. But the understanding is possibly changing in the last year or two. So we could be wrong about this. It's still something which is fairly hard to simulate in climate models. So the climate models, as far as I know, don't agree too well on like these results.
Oh, thank you. And one other question. I read 2 times in internet that there is a volcano under the Antarctic, and this caused the melting the ice. I don't know, is it true or just some news, some journalists make jokes?
Mm. Yeah, I haven't like heard about this particular volcano, but like the major effect is just due to global warming in terms of the melting of Antarctic ice, uh, especially in like over the Antarctic Peninsula and over West Antarctica. Less so over East Antarctica, which is still like it's much colder. The Eastern Antarctica is much colder than the West Antarctica. So it's simply due to increasing atmospheric temperature. So that's enough to, I would say, explain the reduction of the ice sheets. But if there are, volcanoes that could create like a local effect, which wouldn't be like, affecting all of Antarctica, it would be something, very local, but it could be an issue as well. But it's not something that I'm aware of, to be honest.
Yeah, thank you.